We were inspired by the movie The Martian to create a communication device similar to the one Mark Watney created, to communicate with Earth by having a rover that both he and NASA control turn its camera to look at signs planted in the ground to send and receive messages. Since there were too many letters in the English language, he used hexadecimal to better space out the signs to make it easier to determine what letter was being pointed to. In this project, we used a rotary encoder to track where in the circle of letters the motor Cache rover camera would be pointing. We used an incremental rotary encoder which can transmit a motor shaft rotational speed, position, or direction into counts per revolution. It has capacitive sensing technology, so the encoder uses the change in its capacitance value to measure displacement. Additionally, an incremental encoder allows for precise control over the motor. In the selected rotary encoder, the position, speed, and direction are determined by two signals being measured, channel A and channel B. These channels measure capacitance as conductive portions of the disk pass by them. The speed is determined by how many pulses pass by in a specified duration of time. Position is determined by counting how many pulses have occurred and multiplying that by the distance covered in one pulse. The direction is calculated by analyzing if the A signal leads or lags behind the B signal. Additionally, there is a signal Z that tracks full revolutions. Now for how the signal chain won. Rotational movement. Input, mechanical rotation of a shaft. Second sensing element, encoder disk. There are two main types of rotary encoders, incremental and absolute. Incremental uses a disk with alternating transparent and opaque segments. Absolute uses a more complex pattern to represent unique positions. 3. Optical or magnetic sensing.
Yeah.
Optical, an LED shines light through the encoder disk. A photodetector senses light/dark transitions. Magnetic uses a magnetized wheel and Hall effect or magnetoresistive sensors. This converts rotation into a raw analog or digital signal, typically square wave pulses. 4. Signal conditioning. The raw signals, like sine waves or noisy pulses, go through amplification filtering, e.g. low-pass filter to remove noise, Schmitt trigger or comparator to convert analog to clean digital square waves. Outputs, channels A and B, and sometimes Z or index. 5. Digital encoding Gaussian edge detection. A and B channels are offset 90 degrees out of phase, quadrature, allowing direction and speed detection. A microcontroller or encoder interface IC detects rising falling edges, determines rotation direction, counts pulses to determine angle or position. Optionally handles the index pulse Z for 0 position reference 6. Processing, control system. The processed signals are fed into microcontroller FPGA PLC motor controller, etc. This system computes angular position speed by pulse frequency, direction total rotations by counting. 7. Application layer. Final processed data is used for motor feedback, UI control, volume knobs, etc. Robotics, CNC machines. Anything requiring rotary position feedback. Strengths of rotary encoders: highly accurate at measuring rotation, easy to implement in a system. Weakness: needs to be homed every time it's used and cannot hold position data when losing power, and is vulnerable to dust getting inside the mechanism, interfering with contacts and interrupting the signals. A stepper motor has pairs of wrapped wire, coils, and a magnetic core that is shaped like a gear with the teeth being permanent magnets of alternating poles. You can tell which wires are paired together by touching the ends of any two coil wires together. If two wires are a pair, the shaft of the motor becomes more difficult to turn. To run the motor, the coils get sent current, which creates a magnetic field that interacts with the permanent magnets inside the housing. This creates attractive and repulsive forces, turning the armature to align the fields. There are another set of gear teeth in the stationary housing, called stator teeth. These teeth are used to shape the magnetic fields from the coils so that the rotor magnet teeth sit aligned with the stator teeth. Since there are many teeth, the nearest aligned position is not very far. Yes, generally this distance is a couple degrees or less. To move to the next step, the current on the coils that were just powered up to make the strong field is lowered, making the field strength drop. As this happens, more current is supplied to the next coil pair, which raises the field strength of those coils. This advances the core again a small distance. These small distance increments are called steps. In the code we wrote, we can tell the motor to take a defined number of steps with the help of a control board, rather than having to directly control the power supplied. There is also a technique called microstepping. By controlling the current going to adjacent coils, the local relative field strength is manipulated. This way, the gear tooth can be held in place between two stable positions. Half-stepping holds in the middle with equal force on either side, while further subdivisions of
Yeah.
microstepping use a ratio of current to control where tooth is held that approximates a sinusoidal AC waveform. This way, the motor can take fractional steps for even more precision. A housing for the stepper motor was created in SolidWorks and then 3D printed. It would allow for the stepper motor to be slide into it, then the rotary encoder attached to the shaft, and there were holes that lined up with the mounting holes on the wide base of the rotary encoder. A pin or dowel will be put into the lined up mounting holes to hold the rotary encoder in place as the stepper motor moves. This code implements a Martian hexadecimal communication system that controls a stepper motor to position hexadecimal symbols at 20-degree intervals. The system is designed to convert text input into pairs of hex digits and then rotate the motor to display each hex symbol sequentially. The motor moves in the shortest path between positions to prevent cable twisting and includes a homing routing to reset to a 0 position after each character. The hardware setup consists of an ESP32/Arduino board driving a stepper motor, 400 steps per revolution with microstepping, and an AMT10E2-V rotary encoder, 2000 pulses per revolution, for precise positioning feedback. The motor driver is enabled via an enable pin, and movement is controlled using step and DIR signals. The system processes serial input, converts each character into 2 hex digits, and moves the motor to the corresponding positions, spaced 20 degrees apart, totaling 18 positions per full rotation, 16 hex symbols, 1 homing position, and 1 blank. After displaying each hex pair, the motor returns to the home position, 0 degrees, providing debugging feedback via the serial monitor. The code includes functions for homing, position calculation, hex conversion, and motor movement optimization to ensure efficient and accurate positioning. Throughout the process, there were a few issues that came up, such as conflicting schedules, which made it difficult to get an early start on this. Additionally, we had changed our idea during week 5, so we had to do more research. And there were additional changes that were needed to be made, such as we wanted to use either a laser or camera at first. However, we made the decision to not include them since lasers could lead to eye injuries. And the camera was seen as not necessary because the main focus was positional sensing of the dowel, unlike in The Martian, where pictures were needed to be sent between Mark and NASA. During this project, we got to learn a lot about how stepper motors work and how to use them. We got more experience with using Arduinos for controlling motors. To add, it was super interesting to look into all the different applications of rotary encoders. Even though this project worked, please do not ask us to help you escape from Mars. Leave that for NASA to figure out.